Hello and welcome to the lecture Generative Modeling. In this lecture, we first define what do we mean by generative modeling. Then we try to understand what are the different synthetic data generation process. Then we define discriminative and generative learning, and we conclude our lecture by differentiating the generative and the discriminative learning. Generative modeling is basically a branch of machine learning that essentially handles the learning of underlying probability distribution of data so that the new realistic sample can be generated. That means it basically tries to understand or model a given data distribution. These data distributions are given by means of samples. Now let's take an example. If we have 1,000 of images of cats, a generative model is try to understand the patterns of the images. Here the cat images, the structure, variation of those images, the color, the shape and other attributes. And when it is being trained, it try to create the entirely new cat image that was not in the training dataset. In that way, it creates or it has the ability to create a new images that follow a given distribution. For understanding what we are familiar with, normal classification problem, which is basically a discriminative model that learns to distinguish between categories like cat versus dog. That means in discriminative learning or a discriminative model, try to learn the difference between two class of data. Where in generative learning is try to find out the actual distributions of a given data, and so that it can create a new samples that follow that particular distribution. Okay, so in general what we will see that generative models are mainly unsupervised in nature. Okay, and it learns the pattern of input data from a given distribution, as we said, to generate new examples which belongs to the similar distribution. Now if we see a bit statistically, a generative model tries to learn a data distribution of P of x or a joint distribution Px. Why? What is x? X is the input distribution. Why? If available, this level is available. So one distribution is learned, the model can sample new data points from this. One thing it is very important to understand, this create new data points. That means the data points that not belong to the training data, and that's why it's generative. It creates a new data. Okay. Now as we discussed earlier also, why synthetic image generation is required is at this point of time. Now what we have seen in our last part, that in supervised learning paradigm, deep learning become a very important and very successful model, mainly in computer vision and other areas, definitely NLP and medical imaging and so on. In supervised classification, mainly for the deep learning models, it requires a huge data to learn these deep networks. Huge data means huge annotated data. Now, we observed that getting this huge annotated data is always a very costly process, very time consuming process, and sometimes it is almost impossible. Some data leveling or even data are very rare and very complicated to get. So we require some sort of alternative mechanism so that we can get this kind of annotated data or annotated huge data set to learn our supervised deeper models. Here exactly the generative AI or generative model come in the action. Synthetic image generation is an important computer vision because collecting and leveling large amount real-world visual data is often expensive. And this can be done easily by these generative models. So synthetic data helps address these challenges by creating artificial images, videos, or sensor data that can be used to train and evaluate vision models. Now we are trying to understand to some vision specific examples why the synthetic data is needed. Just for example, that what we have said that it reduces the data collection cost. And as we already said, gathering real images and annotating them require thousands of hours of manual work. Now, what does this mean? If we take some examples, let's say a drawing bounding boxes around pedestrian in millions of frames. You can see here, it is just a single frame of a video sequence. And now, if you have to do for a thousands of or millions of this kind of frames, it's a very tedious job, and it requires thousand hours of human time. Then leveling lane marking for autonomous driving. It's also a very cumbersome jobs and requires not only it is costly, it is time consuming. In medical imaging, segmenting organs in medical images is a very critical task and is very costly because some radiologist or medical practitioner should be involved in that kind of job. Now, they are very busy, time is very costly, so definitely you can understand these are costly affairs. Now, if we can generate accurate leveling and generating such kind of images, then it will be very much helpful. Definitely challenging, but it will help a lot of issues. So synthetic dataset can automatically generate levels during rendering, eliminating much of these annotation efforts. Now we see this thing in bit in depth. Now you can see it provides a perfect ground truth. And take an example. If we try to do some noise correction or image or video restoration for underwater scenarios, if you put a camera to a river water, in general river water is very muddy. It is nothing visible, almost nothing visible. Now you can get some degraded image, But only degraded image is not going to work. What is required? Required the corresponding ground truth. And that is very tough to get in actual scenario. So similarly, when synthetic scenes are generated in simulator, that means in lab setup, so the exact object location, object identities, depth information, surface normals, segmentation mask, camera process are already known. So what are those? These are basically kind of attributes. That attributes are very much required for the data when we do these different vision tasks. These attributes playing a very crucial role. So for natural images, getting these attributes or annotating these attributes is a very costly affairs and time consuming affairs. Synthetic data in a lab is very much useful. Already it have these informations. Definitely, these produce highly accurate levels that are difficult to obtain from a real world data. Because most of the time in real world scenario, as we have mentioned in the underwater scenario, we cannot get this ground truth. What are the clear version? Exactly. These kind of attributes is also tough to get in normal scenarios or real world scenarios. Now come to another problem. It solves the rare event problems. What is rare events? That the situation occur very infrequently. That it is we should not want, but car accident happen very rarely. How many such kind of images or videos can get? But we can easily synthesize it. We can synthetically generate this kind of video. Pedestrian suddenly crossing the roads. It's also very rare situations. Industrial equipment failures, severe weather conditions. All these scenarios is very rarely happen. So if we have to train our model to understand or model these rarely events or rarely happening events with this synthetic data generation or synthetically generated videos are very. So a synthetic environment can generate thousands of such, allowing models to learn from events that are rarely captured in real data. So that is another big advantage of synthetic data. Apart from that, the synthetic data improves the diversity because the real dataset may contain biases in certain geographic regions, certain weather conditions, lightning situation, demographics. These are the things. If we have not taken the images or video, considering the diverse situations of these issues, then the images may biased with the sub conditions. For example, if we taken all photographs in a rainy days, or if we take photographs in homogeneous lighting. So synthetic generation can systematically vary. It may be rainy image, foggy image, or image with snow, different times of the day, different viewpoints, camera viewpoints, and the object appearances. So this kind of property helps to model generalize better. Now, it also enables self-training for dangerous application. Some situations are very risky to collect in real-world scenario. Autonomous vehicle crash, military reconnaissance, disaster response, robotics, drone emergency landing. Such and such are very dangerous situation and is very critical to take images or videos of such events. Simulation allows these scenarios to be generated safely. And it also synthetic data support domain adaptation. Common workflow is train the large synthetic data set and find smaller real adaptation, which reduce the amount of real data required with the maintenance high performance. Finally, it helps when privacy is concerned. In real world domain, there is a lot of privacy issues involved, mostly in healthcare, surveillance, retail analytics, and such and such. Real images may contain sensitive information which may not be disclosed to the public. But the synthetic data can mimic the statistical properties of real data without exposing them for individuals. So these are the main advantage of synthetic data for nil supervised deep learning scenario. Now, as we also said, there is several challenges or several problems associated with synthetic data is not a complete replacement for real data because of simulation to reality gap. Now, this is very important to understand. Ultimately, end of the day, these are simulated data. This is not real data. So therefore, there should be some gap between this simulated data and real data. Now, the thing is that models trained only on synthetic images may struggle with real world noise. Now, what data we are generating, it mostly is noise free, but real world data is never noise free. Other thing that what sensors we are using, this particular sensor signature, we can say sensor artifacts, is always with this data. Unexpected object appearance that may be possible in the kind of synthetic scenario. And complex lighting effects is very challenging to get. What is very important, even you can see when we take a normal photograph, there is different kinds of objects, buildings, trees, some vehicles, and it creates a different kind of light and shadows, and it is dynamically changing. This kind of situation creating in a lab setup or synthetical is not easy. So this kind of complex lighting effects is may not be present in synthetic data. So what we'll do to reduce this gap? Some techniques are basically used. Now at this moment we are just name these techniques in this course. will definitely come up with in detail. First of all, domain randomization. That means an image is taken, let's say in rainy day. If this data can be taken in the sunny day, how it is being? So can it is possible that the data, both scenario can be taken. Photorealistic rendering. Make a synthetic photo to make it is more realistic. What are the image processing? GenAI augmentation. It is also important. Fine tuning with real world sample. This is a very interesting way of that we generate data synthetically, train our model, and then do the some transfer learning using the real. Now we are going to discuss different learning models. Mainly there are two types of learning models. One is discriminative learning model and other is generative learning model. Now a discriminative learning model is basically learns by means of discrimination. Let's say there is a two type of events or two type of object like cat and dog. Now a discriminative model that try to model the separation or relation between these two input features or categories and map it to the output levels. What does this mean? Let's say there is a class of cat and class of dog, and there is a some annotated examples or input training data is available. So what it learns from the input data set, it try to learn a mapping function between input to the output. What does this mean? For dog images, it mapped to the label dog, and for the cat images, it output to the label cats. So we can say a machine learning model that learns by discrimination. That means discrimination between cat and dogs, and that means the boundary or relationship between input features and output values. So they essentially learn a mapping function between input images to a output levels. Now it is not going to model or learn the modeling how the data is generated. Rather, it directly learns to predict the target class from the observed data. That is all about a discriminative learning. On the other hand, a generative learning model is a machine learning model that learns how to generate the data. Now, for that reason, it tries to model a given distribution, data distribution, and then generate some images, which images or distributions of these generated images should be very close to this given distribution. So instead of only learning the relationship between input and levels, it learns underlying probability distribution so that it can generate the new data. Why I am saying new? Because these data are not in the input training examples. So as a whole, these two are in a definition level, that these two models are different. Now one by one we see. So first we start with discriminative learning. So a discriminative learning model, as we have discussed, focuses on learning the relationship between an input X and an output Y by directly estimating the conditional probability of Y given X. That given this X, what will be the probability of its target class, or that by learning the decision function fx that maps input to the outputs. It may be the decision boundary, or for a regression problem, it may be a hypothesis function. So, now, if we see a bit statistical perspective, we have a data set, that this data set is a paired data set. X1 is a kind of data. It may be multivariate data. That's why we put vector, and yi is basically class level, and such n number of samples or examples are given. Okay, so xi is a feature vector, y is a class level. So what is basically going to estimate, given x is equal to some sample, what will be the target class of x, and directly from the training data. This is the basic idea of discriminative learning. Now, from the statistical perspective, discriminative learning is about estimating relationship between inputs and outputs directly, without modeling how input themselves are generated. That is very important to understand. Now, as we have said earlier, given this d of x1, y1 to x and y, this xi is a feature vector, y and a class level. The data is assumed from some unknown joint distribution P of x. One thing is very important to understand, that we are saying the distribution, but this distribution is not known. Distribution is known to us by means of a set of examples, of set of training data or annotated data. So what is the task? Task is to predict y from x. That is the task. So a discriminative model focuses only the conditional probability, p, y is pure probability of y given x, without modeling the distribution of the predictors, that means px. A discriminative model learns by directly estimating conditional probability or equivalent landed decision function. That means what I say is a decision boundary or is a hypothesis function. That is basically a mapping function that maps from input to the output. So the examples to the target level. Okay. Now take a example. Now here the discriminative model is basically a classification. So what actually this discriminative model is learning? It model this decision boundary. Okay. Now decision boundary is basically what? Is basically a kind of mapping function that discriminating between apples and non-apples. Okay. Now this function is basically this kind of thing. So this is a logistic function or in logistic regression. This kind of function is been given, and we put a sigma nonlinearity over there to get this. Now, if we said that what is this apple? So it say okay, this is an apple. So that is basically the basic idea of the discriminative function. So this is an apple. So model is concerned with distinguished classes rather than explaining how observation works. We are not interested about this apples distributions or understanding the or modeling this distribution. Rather, we try to understand between this class apples, what is the different attributes of apples and non-apples, so that given a new apple, we can say it is apple. If we say some other food, it's non-apple. So this is the basic idea of the discriminative model. Next, another example that we are going to give, the linear regression. Linear regression is also a kind of model where these data points x1, y1 from an unknown distribution p of x, y, z, you can say these blue dots is basically the data points. Now, what is our task? If a new data point been given, it is x, can we tell corresponding y? Because these points, these blue points, we know the x, y, yi pair. Okay. Now, what is basically we trying to do? What we trying to do that we try to find out a function. Since it's a linear, it is a linear function. We call this function as a hypothesis function. And this function should be very much consistent to this given data. That means it passes very close by to all the data points. That means this. So this function is a straight line because it's a linear regression. The basic process of linear regression to find this line, because this line may be anything. But what we require? We require the line where this line is passes very close by or very consistent with the data points. And how we can do this? We can do, there is some sort of least square fitting. That means the distance between these two should be minimized. So we derive the objective function and we minimize this objective function by gradient descent like kind of optimization, so that we can get this. So linear regression is a simple example of discriminative learning in definitely in supervised case, where we hypothesize a decision function or a hypothesis function from set of training data. Now comes the generative modeling. Now in discriminating modeling, our main goal to find out a mapping function between input to output. Input is a training data, output is variable. We are not interested about the distribution of the training data. But in case of generative modeling, a generative model is a statistical model that learns the joint probability distribution of the data and the target variable. So basically P of y or equivalently P of x giving y. Well, what is definition of this? So what have to understand, unlike discriminative models, which basically learn this conditional probability directly from the given data sample, generative models attempt to explain how data are generated. That we see in our examples. So what we basically going to do, that suppose we have data like this. This is a paired data, this is a annotated data, where xi is a featured data, yi is classified as before. Now we have used the Bayes theorem that we know will come in the next class in detail, but that this is basically this P of x, right? This is P of y by P of x, x given y. So this x given y is called class conditional distribution, and this is the called it is kind of, you can say, this is the distribution of the given. Then it computes y by x by this. So some kind of statistical measure that we try to find out this. Now what we are basically doing, that the data is drawn from unknown true distribution. So basically xy is coming from a distribution that is called p data x. This distribution is given as a sample, but it is unknown distribution we don't. So what a generative model is basically do, it learns the parameter theta of a model, p theta x y, such that this p theta x or this distribution is very close to this given distribution. So basically we try to learn the parameter theta so that we can generate some data, and the distribution of generated data is very close to the given distribution of examples data, evidence data. So generative learning is the estimation of the joint probability distribution that we have seen in the last slide. Now we can write joint probability distribution in this way: p theta y, p theta x y, where theta is the parameters, where py is a class pair and p x y is class conditional. So as a whole, this is the statistical definition of generative models. Now we take a example of generative modeling and try to understand what we have discussed in last slide. Now here we can say the similar setup. We are given a set of data samples drawn from an unknown distribution, real data distribution. So this is, that is the D. I'm taking the MNIST data set. It's available from internet. So this is the real data distribution that we are given. So what is our objective here? To train a neural network. So this is a neural net known as generator, to learn this underlying distribution and produce a new distribution dbar that closely approximates. So this generator, starting from a random noise, and generate some data that is very close to this. So this is the generated data, and this is the actual data. So what is the basic objective? That we generate these data in such a way that this distribution is very close to this. So what generator do? Generator takes a randomly sampled noise vector z, also called the latent vector, as input and transform it into the synthetic data sample. So this. So as a whole, generator start from a random noise, is the latent space or latent variables, and generate this generated data, which is basically closed. To do this, how it should be closed? We train such a way, we find a loss function, that is the statistical distance between D and D, because that is our purpose, to minimize this. So this loss, and this loss is basically back to generator to train their weights and biases so that it generated accordingly. So this is the generative modeling. Now, what happened during training? The neural network is optimized so that the difference between real data distribution D and the generated data D, as what we said. So we define loss functions. The difference is measured in statistical distance metrics, such may be L1 norm, L2 norm. So as the training progresses, the generator gradually learns to produce increasingly realistic samples. What does this mean? Because what the outputs are being generated by generator is becoming close to this, because this distance is minimized. After convergence, the generator can generate new data samples that look, these data samples are not available here. These are new data samples that closely follow the original distribution D while being novel and not identical to any sample present. And that is our purpose. So what is the basic difference between the discriminative versus generative? Discriminative models are trained to find a conditional distribution P of y given x by maximizing this log beta, this kind. Whereas in generative models are trained to get samples from a distribution which is similar to a given distribution. So statistically, x of y is basically this is the true distribution or real data distribution, and we try to find out this theta, that is the basically parametric model of generator. This generative modeling method learns parameter theta of a model this so that this p theta of xy is very close related to the real data distribution p theta xy. So generative learning is an estimation of the joint probability distribution of this data, and joint probability distribution can be written as in this conditional distribution. As p of y is the classifier and p of x given by class condition. So that I'll see this statistical definition. Yeah, later part of this course. So in this lecture, we covered what do you mean by generative modeling, and then what are the advantage and disadvantage of synthetic data generation. Then we discuss about discriminative learning and generative learning, and we conclude by defining the difference between generative and discriminative learning. In the next part, we'll focus on generative vision models. Thank you very much.